Hey physics friends, Mr. Collier here. Today we're going to talk about circular motion. Up to this point in the year, we've been talking about translational motion, which is motion in a straight line. And now we're going to start talking about things that are moving in circular patterns. Just to get two quick terms out of the way, a rotation is an object that is spinning about an internal axis, like the Earth rotating on its axis to spin around, causing day and night, versus a revolution is about an external axis, like the Earth going all the way around the Sun, where the axis of rotation is the Sun, which is outside of the Earth, and that's what causes the year to go by. The Earth is a rigid body where it rotates with all of its parts locked together without any change in shape. We're going to stick to this, looking at things like, wheels and disks spinning around. It does get more complicated with things like the sun, which are sort of plasma-y and don't actually all move at the same pace. And we're also only going to talk about things that are on a fixed axis, which means the axis does not move. Every point of the body moves in a circle and around that axis of rotation. So another shift we need to make is up to this point in the year, we have been talking about Cartesian coordinates, an x and a y, where is an object, how is it moving. Now we're going to start talking about polar coordinates. Polar coordinates are going to use the radius and theta to talk about where an object is. We also are going to need to, throughout this, remember that the circumference of a circle is 2 pi r. So what this is going to look like is we're going to shift from looking at x and y to looking at where an object is in terms of its angle and the radius of the circle it would be on. And as we learn to convert, you're going to want to remember this, maybe even add it to your equation card, that our x-coordinate is equal to r times the cosine of theta, and our y-coordinate is equal to r times the sine of theta. And I'll show you that in a sample problem here in just a second. So I'm going to show you how to convert to and from polar coordinates. In this case, we're starting with Cartesian coordinates, 2 meters and 3 meters, and we want to figure out what the polar coordinates are. So if we have 2 meters and 3 meters, what we want to do is figure out the r. We're simply going to use Pythagorean theorem. So r squared is equal to x squared plus y squared, and so we can plug our numbers in to figure out the radius of a circle that has those two Cartesian coordinates as part of it. We also then, knowing that x is the adjacent side and y is the opposite side, then we can discover theta by taking the inverse tangent of y over x. Another thing that we're going to be doing several times in this chapter. And so we plug that into a calculator and we find that this is 56 degrees, this angle. And so therefore, we put it together and our polar coordinates are 3.6 meters, that's the radius of a circle, and 56 degrees. We can also go the other direction and start with polar coordinates and turn them into Cartesian coordinates. Here where 3 meters is the radius and 40 degrees is the angle, and we want to figure that in terms of x and y. So we know the radius is 3 meters. Our x side is going to be the adjacent to that angle, and adjacent sides use cosine, so we're going to do the cosine of x over 3. And this is actually where I got that equation earlier in the slideshow, that x is equal to r cosine of theta. That's where that came from. I'm just rearranging this definition here. And so we solve for x, and it's going to be 3 cosine of 40, and we get 2.6 meters. We can do the same thing for y, but since it's opposite, we use sine instead of cosine, and we solve to get its length as well. And that leaves us with Cartesian coordinates of 2.6 meters and 1.9 meters. Something else we need to talk about when talking about circular motion is this thing called angular position. We're talking about how objects move in terms of spinning. So we need to identify the axis of rotation, and then we need to create some sort of reference point, usually a fixed line through an origin point, and we call that 0. So from an overhead view, we would be like, here is where the object is starting, and as it rotates, it's moving, this way. by defining that origin and that rotation, we can start to understand things. So now that we're looking at it overhead, we need to understand that it's going to have some sort of radius, and then as it spins, it's going to trace out some distance. That distance on the outside of the circle is called the arc length, and we abbreviate that with an S. So we've got S and R, and we're going to go back to something you might remember called radians. When the radius of the circle is equal to the arc length that it sweeps out, that is defined as 1 radian. We can then create an equation that tells us the angular position, theta, where theta is equal to S over R, the arc length divided by the radius. And that will give us our answer in radians. So if they're the same number, any number divided by itself is 1, that would be 1 radian. So when the, again, swept out area equals the radius, that's 1 radian. We can then set up some definitions, right? A full revolution going all the way around, we know that's 360 degrees, right? That's also 2 pi radians. We can also then solve for 1 radian. We can say that 1 radian is 57.3 degrees, which is 0.15 revolutions. These are some very common conversions you're going to want, so you might want to jot them down on your equation card. So using these definitions, we can actually do some conversions. We can convert 75 degrees to radians. We know that 2 pi radians is 1 revolution, that's 360 degrees. So pi radians is half of that, that's 180 degrees, and that 1 radian is 57.3 degrees. So we can use that information to convert. We can do 75 times pi radians over 180 to get 1.3 radians, or another way to write that would be 75 degrees divided by 57.3 degrees per radian. Either way, you're going to get the same answer. It's a couple different ways to write it. We can also convert the other way from a number of radians to degrees, 2 pi over 5 radians, and then we're going to multiply that by 180 degrees per pi radians, or multiply it by 57.3 to get the number of degrees. Finally, we can use this to make some calculations and some problems. So say that in a NASCAR race, we're observing that there's a 100-meter radius in the curved part of the track, and that the straightaways have 3,000 meter straightaways, and we want to find the total distance of the track. So we know that there is some arc length traced out here that we want to solve for. That's S. There's the same amount over here, and then there's these 2 straightaways that we're going to add in as well. So we know that half a circle is 180 degrees, or pi radians, and we know that that radius is 1,000 meters. So we can rearrange the equation and find S, the arc length, the distance along the actual track, is equal to R times theta. So the R is 1,000 meters. We're multiplying it by pi radians, and we get 3,141 meters, but there's actually 2 of them, so we multiply by 2. Then we're going to add in the 3,000 meters twice to get our total length. Or you might have just realized at the beginning that 2 half circles make 1 circle, so you might have just multiplied it by 2 pi, which is a full circle of radians. So that's it for circular motion. Now you're going to start in on your first homework. Good luck.